Okay. Good afternoon, everyone. Welcome to Creative Weekend Talk of episode 183. I am Supriya, your host for the day. At Creative, our vision is to promote constructive thinking across various domains. We focus on no, non-textual, non-academic, non-syllabus related. Sorry. Creative. Vision of Creative is to promote constructive thinking across various domains. We focus on non-textual, non-academic, non-syllabus concepts, creating a space for insightful exploration and meaningful conversation behind the classroom. Today's topic, unsolved conjecture and their role in mathematical research, take us into a fascinating world of mathematics. We will explore how open problem continues to shape and challenges the direction of research, fueling both innovation and discovery. We are delighted to welcome our today's speaker, Srimati Vidya Shri, Assistant Professor, Department of Science, Nagarjuna College of Management Studies. Her passion for mathematics and academic experience will help us to better understanding. As always, we live stream our program on Creative YouTube channel, Creative GBD. So, feel free to revisit the talk or share it with the others who may find it thoughtful. And I welcome today's speaker and all the participants for the today's session. And I call Uma Devi to introduce today's speaker. Over to Uma.
Thank you, ma'am. A very good afternoon to everyone present here with warm greetings. It is indeed a great pleasure to extend a warm welcome on behalf of Reactive team conducting a wonderful webinar on unresolved conjectures and their role in mathematical research by a resource person, Srimati Vidyashri HR ma'am. Ma'am pursues a profession associate professor in Department of Science, Management Studies, Chicago. Ma'am has pursued her master's in mathematics along with B.Ed and PhD. Ma'am has ample experience in teaching as she worked for high school mathematics, UG, BSc and BCA and PG, MCA and MSc mathematics students. With a great geniality, she conducted many workshops which includes conducted a Python programming workshop of 50 hours for BSc students at NCMS, delivered a talk on the essence of mathematics in computer applications, presented a talk on applications of mathematics in various fields, delivered a talk on the versatility of mathematics applications in technology and beyond, presented four research papers at international conferences, participated in 13 national and international conferences, and many more. Our ecstatic and enthusiastic guest has been awarded with certifications like Mathematical Science Refresher Course, NPTEL Elite on Graph Theory, AI for All, Python Essentials 1, MATLAB on RAM, LaTeX Hands-on, NPTEL on Patent Drafting, NPTEL Elite on Intellectual Property, and many more. Cheers to you, ma'am. And once again, I welcome you, ma'am. I extend my welcome to all the Creative members and all the inquisitive minds gathered here. Welcome you all. Thank you, ma'am.
Thank you, Uma. Over to you, ma'am.
So, good afternoon, everyone. Thank you, Supriya ma'am and Uma Devi ma'am, for introducing me to the audience. So, today I will be talking about conjectures. My topic is unresolved conjectures and their role in mathematical research. So, let me share the screen first.
Visible, ma'am.
Yes. So yeah, my topic is unresolved conjectures and their role in mathematical research. So there are numerous conjectures in mathematics which are unsolved, which don't have formal proof even now. So here in my presentation, I have taken few conjectures from number theory, and I will be, explaining what are those conjectures, what are the recent advancements made, and what will be the future in case if we can come up with the formal proofs, and what are the applications of these conjectures. So to begin with, so my topic is all about conjecture. Now, what is conjecture then? A conjecture is an unproven mathematical statement believed to be true based on the evidence and intuition. So, conjectures, though we don't have formal proofs, we intuit. With the intuition, we proceed with the further research on that, believing it to be true. So this inspires research. We have come up with many new methods. We mean the sense mathematicians have come up with many new methods in order to prove them. And many other disciplines like computer science, biology, chemistry, all have been connected in terms of proving this conjecture. So there is an example for this. There was a theorem called Fermat's last theorem, which was actually formulated in the year 1637, and it was proved in 1994 by Andrew Wiles. So it took almost 350 years for a mathematicians to prove the theorem. So in this particular presentation, I'll not be talking about Fermat's last theorem. It is just an example how the conjectures, how long it may take for mathematicians to prove it, and what are the possibilities. So in this presentation, I'll take you all through three major conjectures from number theory. So first one is called Goldbach conjecture. So the conjecture states that every even integer greater than or equal to 4 can be expressed as sum of two prime numbers. So you consider any even numbers which is greater than 4 that can be expressed as sum of two prime numbers. So there are few examples listed here. You can just go through. So 8 can be written as 3 plus 5, 10 can be written as 5 plus 5, or 3 plus 7, lot more. So there are many examples as such. So the statement is, we have, though we have many examples to prove this, we don't have a formal proof to state that this conjecture holds good. So when we look at the history, this particular conjecture was proposed in 1742 by Christian Goldbach in a letter which was written to Euler. So in process of proving this, mathematicians have come up with two different Goldbach conjecture. One is binary, which I have just now discussed. So the even numbers that can be represented as sum of two prime numbers, that is nothing but binary. And we have something called ternary, which talks about odd numbers greater than 5 that can be represented as a sum of three prime numbers. So this was actually introduced in 1937 by a mathematician called Vinogradovs. So I'll explain it. When we look at the history, we can see that, as I told before, this conjecture was proposed by Goldbach in the year 1742. Hope you can see all these things here. So to highlight, in 1937, the mathematician called Vinogradovs, in one of his theorem, he came across, or he introduced, ternary Goldbach conjecture. Luckily, in 2013, mathematician called Helfgott could able to prove this, which means that he has given some formal proof for ternary Goldbach conjecture. So again, binary Goldbach conjecture is still open. We don't have any formal proof for that. Yeah, we have some applications, we have some graphical representation, all those things, but still we are lack in finding or giving formal proof for binary Goldbach conjecture. So in recent advancement, if we can look at it, as we know nowadays, AI ML methods or models are many to solve many of the problem statements. So when we look at the conjectures, yes, we do have some models to solve this conjecture or to come up with examples for conjectures. Though we all have all those things, but still we are unable to go beyond 10 to the power 18 numbers. So in spite of having computations, in spite of having all those AI and ML models, we are unable to go beyond some numbers. So that's an open statement. Now I will take you through one of the graphical representation. So this is a representation which was made by one of our student. So here in this paper, what they have done is like any even number, it could be binary or ternary, even or odd numbers. If you look at the pair of prime numbers to satisfy the Goldbach conjecture, there are many options. It is not like only one pair can give that particular even number. So if you look at this example, when n is equal to 18, if you don't consider commutative property, we have 4 different options. So one is 5 plus 13, 13 plus 5, 7 plus 11, 11 plus 7, like this. Now, if you can look at ternary example, which is given here, 19 can be, given 3 different pairs, triples of primes to satisfy the Goldbach conjecture. So like this, they have come up with a graph, something called cross-line graphs. This graphs, they have named it as cross-line graphs. So like this, many mathematicians have represented the conjecture through graphs, to tree, many other options. But still, we fail in giving formal proof. Fail in the sense the research is still going on. So probably in future, some mathematicians could give proof for this. So going forward, this is our second conjecture, which is twin prime conjecture. So we all know what is twin prime, right? So you will take any 2 consecutive prime numbers and the difference is 2, then we call it as twin primes. Now, what does this conjecture say? This statement is there are infinitely many prime pairs. So twin primes, when we look at that particularly, so there is no end, there are, as we know, numbers are infinite. So prime pairs are also many, infinitely many are there. This is what the conjecture says. Now again, the same status for this. Though we have come up with many examples or many different numbers of pairs with different ranges, we were unable to give a formal proof for this conjecture. It is still ongoing research topic. So examples are given here, and this conjecture came into existence same like Goldbach in 1942 in the same letter which was written by Goldbach to Euler. So if we look at the, when the mathematicians were trying to solve this or trying to work on these conjecture, they have come across 3 prime pairs. One is twin primes, which I have already discussed right now. The other one is cousin primes, where 2 primes in for which the difference is equal to 4. Then we call it as cousin. If it is 2, then twin. 4, it is cousin. In case the difference is given as 6, then we call it as sexy primes. So these are the 3 prime sets which mathematicians have come across, and even now the research is going on these things. So the mathematicians were trying to build some models and algorithms to find how many numbers of such pairs are available in given range. So this is still going on. So if we look at the history of twin prime numbers, as I told you, this came into existence in 1742. And then if you look at the recent advances on this particular conjecture, there was an exploration of prime constellation. This came into existence in 2021, where they're trying to find out how many numbers of prime pairs are there in between the range using some models. And then AI and ML models are deployed to find prime gaps between the numbers. And then in 2024, this is a recent development, and they have found a large known twin number. So this is up to here, the research have done successfully. So beyond that, the mathematicians are trying to do it. So again, formal proof is still open for this conjecture as well. Now, we will see one more example for this. how a graphical representation could help us in solving these particular conjectures. Not exactly solving, at least to understand the conjecture. So this is an example of graphical representation. Here, they're trying to find out how many prime pairs are there, twin primes, cousin primes, and sexy primes are there between the given range. So in the first image, you can see the range is between 0 to 99. And in the second, you can see 0 to 1000. So number of primes, pairs it is. It is not exactly number they have given, prime numbers. It is number of twin primes, number of cousin primes, and number of sexy primes between the given range. This was recently done by one of our students. So this is actually a present status of this particular conjecture. So usually cousin, they may represent it graphically. They have not tracked it computatively, but twin primes and sexy primes are active research areas. So when it comes to sexy primes, they have come up with something called triple sexy primes, where three different prime numbers will be, three different sexy primes numbers will be given, and they're working on it by constructing a graph, by coming up with some models, algorithms, all those things. So the third one is Collat's conjecture. This is a famous conjecture which is very active from the decade, and this fascinates all the mathematicians, not only mathematicians, in fact, in all the disciplines. So this is conjecture is nothing but a sequence generation process which involves two rules. Okay, you start from any number. If the number is even, then we will divide that number by 2. If it is odd, then we will multiply by 3 and add 1 to it. So if you keep on doing this process, these two rules, if you keep on doing it, then ultimately the number reaches 1 and enter into a cycle. This is what Collat's conjecture says. So you can see the statement there. For every positive integer n, this sequence will eventually reach 1. So again, many mathematicians have come up with graphical representation, many pattern generation, chaotic theory, everything. But till now, formal theorem, formal proof is not available. But few of the mathematicians have provided the proof, like induction method or some different types of proof they have given. But it is not globally accepted till now. So this is one of the example. This is one of the example. So I'll start from 10. And we know that 10 is an even number. So we will divide it by 2. We get 5. 5 is again odd number. So we will apply second rule. That is 3n plus 1. We get 16. 16 is even. Divided by 2. We get 8. 8 is even. Then 4. 4 is even. Again 2. Then 1. So once we reach 1, 1 is an odd number. So we will apply second rule. That is 3n plus 1. Again it goes to 4. So though you have started from any number, it could be any positive number, once that number undergoes the Collat's transformation, it reaches 1 and enter to the loop. This is what the Collat's conjecture says. Okay. So we'll see how mathematicians could able to represent this. So this is one of the representation done by mathematician Daniel in one of his paper. So you can see that though the number have been started from different numbers, the initial points are different there, but still once it undergoes the Collat's process, it reaches 1 through 16, 8, 4, 2, 1 and then enter to the loop. So many advancements were made in this process. So if we look at the history of this, this was actually proposed by Lothar Collatz in 1937, and this conjecture is also known as 3n plus 1 problem. So there are many names, in fact, for this conjecture. So this was theoretically pushed up to 10 to the power 18 number, and recently this through the computation verification, this verification of the numbers were pushed until 10 to the power 20 numbers. But beyond that, the research is still on, and we don't have formal proof which is globally accepted. So yeah, you may ask, there are many proofs are available in research journals, but it is not globally accepted. They would have made some assumption and then they have drafted the proof. That's the reason probably these theorems or proofs are not acceptable yet. It is still an open problem. So recent days from 2020s, what happened is these conjectures nowadays they've started representing through graph theory and started studying those graphs, whatever the representation made by collates. They started studying those graphs and trying to find the existence of that particular graph. They feel that through that they can prove the collates conjecture. This is the concept. So in 2019, one breakthrough was made by Terence Tao. So he came with the concept called almost bounded. So numbers, wherever they start, it will be almost bounded. So here in our collates conjecture, 1 is a least bound because every number reaches to 1 and 1 is a small number as considered for this sequence. So that is a least bound. But this particular breakthrough is not exactly for collates. For general number, they have made it, but this can be considered for collates in particular cases. If we come up with different cases or assumption, then that can be considered. But still, as I told, it is not globally accepted. Okay. So these are the beautiful patterns generated by collates conjecture. Why mathematicians are fascinated, I said, because of this. If you can see those representation or the graphical patterns, it is very beautiful. So one of the mathematician called Kaziabu, he tried to generate a pattern through collates process, and this is the output of that. So beautiful it is. And then this is one more representation of collates process, and this one. So I have taken only 4 graphical representation, and there are n number of graphical representation of collates conjecture. So till now we have seen how positive numbers can be deployed to a collates transformation and see how it reaches 1. Now, what about the negative numbers? Now, we do have negative numbers in the system. No, we cannot ignore that negative numbers. Now, what do we do for negative numbers? So we have, or some mathematicians have already applied the same transformation for the negative numbers. But the thing is, negative numbers may not reach 1, but they enter to 3 different loops. One is from -17, -5, something like that. Okay. 3 different loops they are entering. So what we have done in our work, we have taken a negative number and converted that to a positive number using 2's complement. So hope everyone knows what is 2's complement. So to brief it, a negative number, whatever number we have taken, that number has to be represented in binary number system. Then we will reverse the units and then add 1 to it to convert to a positive number. So here example I have given -14. After undergoing 2's complement, it is converted as 242, which is a positive number. So to that positive number, we have applied collates conjecture transformation, and then we have arrived that even the negative numbers can undergo collates transformation when it is converted to a positive. So this is a flower pattern generation which we made it to represent all collates process sequences, and it's very beautifully, you can see that's flower pattern, colorful. And then we have come up with one another concept, like all the sequence we try to represent that through a graph, and the graph looks like this. So as I told you, any number you start with, it reaches to a loop. So here I have taken a cycle of 3, which I consider that as a loop. And then this tail is a numbers sequence, how it is generated according to the collates process. So in general, we can see this. So any number you start with, here we have taken 2 to the power n, but any number, positive number you take, it reaches to 16, 8, 4, and then enter to a loop. And we have named this particular graph as Ananta graphs. There is a reason behind Ananta, because Ananta graphs consists of 2 parts. One is elongated tail and the other one is triangular head. And this triangular head is common for all the numbers because it enters the cycle. And this elongated tail, depending on the number, it elongates how much ever steps are there, how much ever sequences are there, it depending on that, it elongates. So because of this elongation, we have given Ananta, which means infinite. And then we are trying to prove this conjecture by showing the existence of Ananta graphs. So we have seen these three conjectures I have taken for today's presentation. Now, we see so many conjectures are there. When so much difficulty, why do we need to prove this theorem? One of our students were asking, ma'am, it is so difficult to, come up with a proof, then why we need to prove? What is the need of it? So there are vast applications of these conjectures if it is proved. See, many mathematicians with the intuition, they have come up with many applications already. They already come up with some applications. But in case if we can prove this, then the applications goes to next level. So when we look at how these conjectures could help us in mathematical research. So first one is advancement of mathematical methods. So in order to prove this, or in the process of proving these conjectures, we have developed a new methods, to algorithms, to models. Many concepts have been developed in order to prove this. So in that, if I see sieves method, hopefully everyone remembers Eratosthenes sieves, which is used to identify prime numbers between the given range. So this was actually developed while proving Goldbach's conjecture, which is all about prime numbers. So even now this activity is being conducted. And we have one more method, sieve method, which is called Brunn's method. This estimates number of twin primes up to n. So if we give some range, how many twin primes are there in between that? So that is nothing but Brunn's sieve. So these are two activities or methods which were developed in the process of proving the conjecture. And next we have something called exponential sums. So here also exponential sums, many methods or many sums or formulas have been generated. One is Wien sum and the other one is Vinogradov's theorem. So as I told you, ternary Goldbach's conjecture was introduced in Vinogradov's theorem. So in the same theorem, they have come up with some exponential sums. So all these developments or new concepts were came into existence only in the process of proving these conjectures. Though we couldn't come up with the formal proof, we were able to come up with many activities or methods, new concepts. So next one is circle method. Even now, this circle method is being widely used and applied in many of the fields. So what is the circle method? So this circle method is used to estimate the number of represents of number as sum of other numbers. So it is directly related to Goldbach's conjecture. So in Goldbach conjecture, we saw that a number can be represented as sum of two prime numbers. So here in circle method, it is not exactly prime numbers. In general, any number you take, it can be represented in different ways, sum of different frequent numbers or some patterns. So that is what circle method says. And as I told you, there's a lot of applications of circle method which is still going on to study the properties of numbers, to predict the sequence of the numbers. We use the circle method. Next, probabilistic models. So many probabilistic models have been developed in order to predict the existence of the number pattern or the sequence or the conjectures, all those things. So among that, the famous is Cramel model and we have Edo's theorem. So how a number behaves, probability of the number behavior. So these models helps in finding those things. And then we have dynamical system theory. So it is directly related to Collatz because though we start from any number, it keeps on moving according to Collatz transformation, which is really very difficult to predict if you don't know the conjecture. I have explained. So if I ask you to find out the next number, it is very easy to come up with. But if you don't know the conjecture and you have to find out the sequence, it is really very difficult. So that gives arises of dynamical systems theory. So we have come up with a new topic called systems theory, dynamical system theory, how the number moves up and down. So that's what it says. And next is computational number theory. So according to me, only with the mathematics concepts or mathematics subject, it is really difficult to solve all these conjectures. So other disciplines like computer science may help us to prove these theorems or prove this conjecture. That is what mathematicians are doing nowadays. So they have deployed computations to the conjectures, to all other open problems in order to find whether it is true or not, or if we can come up with any counter examples, all those things. So this give rise to computational number theory. So when we look at the second application is a very famous application, cryptography and security. So prime numbers are the backbones of cryptography. In order to generate, private keys, to generate random number, we use prime numbers are widely used in these processes. So we have prime generation algorithms. So we have come up with an algorithm where randomly the prime numbers are picked, or if the sequence is given, then how to randomly pick or to find the prime numbers using these algorithms. So that is what prime generation algorithm says all about. Next, random number generation. Random number generation widely used in coming up with encryption techniques. So we know that cryptography works on encryption and decryption process. So when we are looking at encryption process, if we want to generate some key randomly, which will be difficult for another user to identify and decrypt, then we always prefer prime numbers as a random to generate a random number. And then we have secure key generation. So public key, private key, we have some concepts law called public key and private key. So where secret keys generation also involve prime number generation in that. So that would be more helpful. And particularly the conjectures. It is not only prime numbers. Using conjectures, you can. So in further slides, I'll be showing one of the examples like how cryptography take help of this conjectures in generation of encryption and decryption techniques. I'll be showing it later. Okay. Then coming to third, we have algorithms, algorithm design and computer science. So there are many algorithms, as I told you before. Algorithms have been generated in the process of proving this conjecture, and that algorithms have been applied to other problems to solve them. So many examples are there. So one among that is halting problems research. So this is produced by Alan Turing. This is generated to understand the limits of computation. Now, halting is nothing but pause. So when you are executing or when you are computing some algorithms, how will you stop that or give a constraint so that that halts, that stops without running infinitely. So that particular algorithm is given. And then we have program termination analysis, same like algorithm, what I said. Some programs will be running when we have huge data. It is difficult to terminate a program. So we have some analysis for that. We have come across some analysis by using conjectures. Like for example, if you take Collat's conjecture, though you have start from any number, all the number ends with 1. So that becomes a constraint. So something like that. Then we have loop optimization. This improves the performance of loops in a program. So optimization is nothing but minimizing and maximizing. So here, depending on the event, whether to minimize or maximize, this algorithm will be helpful. And then randomized algorithms to pick random numbers that influence our decision. So how are you going to pick the random number and how that affects our algorithm or the events? So these algorithms have come into existence by proving these conjectures. So next, chaos, complexity, and unpredictability. Unpredictability, yes, as I told you, Collat's conjecture, if you take an example, in whole process, I'll be talking more about Collat's conjecture because that we have worked on it. So unpredictability, Collat's conjecture, if you take, if I give a sequence where you need to fill the gap, unless and until you know the conjecture and you know those two rules, it is very difficult to predict what will be the next number and to fill that gap. So all the conjectures, in fact, all the conjectures are unpredictable. You cannot predict what is happening next unless and until you know the process and you know what what is determined, which conjecture has been determined there. Okay. And then complexity, yes, all these conjectures, if you have observed, it's very simple to understand. It's very beautiful. That's the reason they fascinate mathematicians. It's very beautiful and simple. But when you dive deep into it in process of proving, that becomes a complex process. So that's the reason complexity is more this conjectures. And then chaos. For chaos, I would suggest Collat's conjecture because it behaves a chaotic, it has a chaotic behavior because it moves from simple to complex methods. So if you have observed those graphical representation or patterns, if you see, since I have explained, you know that those patterns are from Collat's. If you don't know anything about Collat's conjecture and if you look at those patterns, it is really difficult to predict what is going on, and it seems to be chaotic behavior of any number. So these are the applications, and there are a lot more applications we can apply these conjectures in graph theory. We can apply these conjectures in game theory, chaotic theory, fractal geometry. Many are there. So as I told you earlier, I will be discussing about two major application. One is cryptography, then the one is game theory. We'll see how cryptography can be, the techniques can be developed using conjecture, and how game theory will be useful in this process. So if we see the first case, we will talk about cryptography. So here is an example. If you see the first image, here we have given encryption key as 5, and we have given some plain text, and iteration is 5, and then we have got some ciphertext, then decryption key, and then the text, original text. Now the process, let me first explain what is the process. So cryptography is, you will have some plain text and you need to send the message to someone else, then you will deploy some encryption key. So using that key, the plain text, whatever you are giving, that will be converted into ciphertext, which is non-understandable. You cannot understand, you cannot predict what is it. And then you will send a message, and the other person at the other end will receive the ciphertext, and if they know what is the key that you people have deployed, if they use the same key, then that ciphertext will be converted to plain text. So that is a process of cryptography. Now, how conjecture has been helpful here? So in this particular example, we have deployed Collat's conjecture. So we have taken few plain text, and here the plain text has been, we have taken Unicode of all these letters, and then that encryption key 5 we have added to that particular Unicode key, and whatever value we get after adding, we have converted that through Collat's process. And here iteration is 5, which means 5 steps we will be doing. So 5 different steps, though it is not ending at 1, whatever it is, we will stop at 5 iterations. Okay. And then that will be converted. If you look at or observe that ciphertext, it is really very difficult to predict what is the message. So many numbers and so many sequences. If you observe, there is no proper sequence followed. You cannot predict anything. You cannot identify how many letters are there, how many words are there. So this is a beauty of cryptography with Collat's conjecture. And then encryption key is 5. They have added 5 to Unicode. Now what happens in decryption? If we know what is the key, the reverse process of encryption is nothing but decryption. So there they have added, and here they have to subtract it. So that is where you get the original text back. So this is the beauty of Collat's conjecture. And then in case if you don't match the key, what happens? Look at the second image. So encryption key is 6, but decryption is 7, where this is not matching. So you will not get any decrypted image or decrypted content, whatever the plain text was there. So this is the advantage. Here we have deployed Collat's, but many other conjectures can be deployed for cryptography. You make it in complexity, So another example is game theory. So before explaining what is those images, let me just explain what is that problem is all about. Okay. So here we are discussing about rendezvous problem. So there is a problem in game theory, which is called rendezvous. So that states that though the agents start from many initial points, they have to reach at one particular point. They'll start from anywhere else. They have to reach at one particular point. So that point we call it as rendezvous point. And the problem is, when they will reach, do they really reach to one particular point, or they really meet at one particular point, or how long it will take for an agents to meet at one particular point? So this is the problem. So there are many other strategies have come up. Now we have deployed collatz here. So what I have done is, I have considered two agents. You can go with more than two also. So I have taken two agents, and this particular example is asymmetric. There are few definitions. I'll just orally I'll tell you. So this particular process is asymmetric. Asymmetric because they both start with different initial stage. It is not same, different initial points. If you can see the example, one is started with 18 and one is started with 35. So different initial points. And then it is deterministic because we have given them predefined algorithm, which is nothing but collatz. Both of them will be following collatz, but they don't know each other's point. Agent 2 will not be knowing where agent 1 is starting. The same with agent 1. So they don't know where they're starting. The initial point is unknown for both of them, but they follow predefined algorithm. And then both synchronous. Yes, they meet because collatz process, that is what that says. Though you have started from any number, it reaches 1. So that is the collatz conjecture says all about. So it is synchronous. So it is asymmetric, deterministic, and synchronous. Now let us look at the example. So here I have started agent 1 from 18, agent 2 from 35, and it both undergoes collatz process individually. And you can see the second graph. Both meet at 1 after 20 steps. Though, second agent may reach early, but first agent will take 20 steps to come to the same place, which means they meet at after 20 steps. So this is one of the advantage. Why do we need all these things? We should know the applications before we learn anything. No? So this rendezvous problem, if we can solve, there are many applications. One is search and rescue operation. So if one person is in danger and we need to reach them without having, nowadays, yeah, Google Maps are there, but still there will be some condition where, we cannot use all those things. And that would be a challenging for us to meet them. So at that particular time, this process would be helpful for us. And then swarm robots or drones charging point. So robots and drones, if they all can come to one particular point for charging, then what is that point called? Rendezvous. So that problem also can be solved. And this EV station, charging station, all those are the examples of applications of this rendezvous problem. So these are the only few examples like how collatz or other conjectures can be deployed in application process. So there are many other applications where you can come up with cyber security and neural networks. Many are working on neural networks as well. How can we deploy the conjecture? So you may ask me, like, though we have not proved this, how can we apply them to practical, content, practical scenarios? So that is what I said. If you look at Fermat-Last theorem, it took 350 years to solve. So these conjectures, we don't know. Few may come up with the formal proofs as early as possible. Few may take decades. So we mathematicians, instead of waiting for them to get proved, we move with the intuition that these conjectures are true, and we come up with the applications. Till now, we couldn't find out counter example for these conjectures. If we come up with some counter examples which states that this is false, it becomes easy for us to disprove the theorem. But till now, we don't have any counter examples for these conjectures to be false. So that's the reason we mathematicians, we assume that these conjectures are true, and we start exploring in that process. And as I told, it is not like mathematicians have not given the proof. They have come up with many proofs, but it is not globally accepted. So this all are open problems. So what I can say is conjectures remind us that math is a living and evolving field. Yes. So if you can look at any discipline, mathematics is the base. If you can look at AI, ML, usually our computer science faculties would be saying that, all the algorithms which are generated now and we are using for ML are being developed by mathematician or mathematical concepts. So there are huge applications of mathematics which we have to explore it. These conjectures, they challenge us, inspire creativity, and open new doors for discovery. So that is what I said. Only with mathematical concepts, these conjectures are really difficult to prove. So what nowadays researchers are doing is they collaborate with other disciplines like computer science and major other disciplines and come up with some applications or some examples or some graphical representations or computations, all those things. But still, unless and until you give a proof, a conjecture or a theorem cannot be proved. You can come up with numerous examples or numerous bounds, but still it is an open problem. These are my references. Only few I have taken. As I told, there are many other graphical representation. So this ends my session. So any questions? See, I do not expect only questions. I am expecting some queries or suggestions, please, because I can see many discipline faculties are there. Many other faculties from other disciplines I can see here. So if we can collaborate with your subjects, it would be very helpful. Any suggestions or any insights, please, I'm open to it. Queries, please.
Okay, thank you, ma'am. Any questions? Or you can unmute yourself and you can ask the questions.
Hello, I'm Mallesh.
Yes, sir, please.
I just wanted to share with you that the nice lecture that I didn't know that even conjectures which are open can be used for exploring something more like this. So I'm happy that you also mentioned about the application of conjectures in chaos. One is there are two comments. I was once trying to write these prime numbers. I found that 6n minus 1 and 6n plus 1 generally contain twin primes. Is it a general truth? That is my first question. The next question is on chaos. In chaos, we consider nonlinear equation. So at least you should have three variables in deterministic chaos. So can these conjectures be, if they are related to chaos, are there any nonlinear equations behind them? Can one think of like that? That's my query, as you wanted it to be. Thank you.
Thank you, sir. So as you mentioned, the 6x plus n, 2x plus n, all those things are the developments of Collat's conjecture. Yes, I agree. Because in many of the papers, I know in the process of proving, they have come up with some other, representation of the numbers. One among that is 6x plus n, whatever you said, it is true. And that again cannot prove the Collat's conjecture. So it is still open. As I told you, many methods and many concepts have been come up, and that is also one among them. And chaos
So
theory.
I mentioned about 6n plus 1 and 6n minus 1, twin prime, right? That was my reference.
Okay.
All our twin primes can be written as 6n plus 1 and 6n minus 1.
6n minus 1. Yes, sir.
Yeah,
even I have gone through it. Yes, I have gone through it. That's true. That's a good advancement actually in a prime number concept. Yeah. And when it comes to chaos theory, sir, even I have not explored much about chaos theory. Only thing is, what I can say, Collard's pattern can be modeled as chaotic theory because those number has chaotic behavior. So beyond that, even I have not explored chaos theory. So I will explore it.
Thank you. It was a nice lecture.
Thank you, sir.
Any more questions? I think we can end it here. I think no questions anymore. Ma'am,
Yes,
it was excellent talk. We are very fortunate to have you here. Thank you very much, ma'am. Thank you very much, one and all, for joining with us.
Yeah, thank you
Thank
for
you,
this opportunity, Supriya ma'am and Creative. We
We
really
have
very
to thank
happy to be
Ajit
part
sir
of it.
also.
Yeah. In this many advances, Ajit sir have helped me. So thank you, Ajit sir. He's probably
Okay.